Have you ever wondered how your electronics just work? How does your phone charger turn the zappy stuff from the wall into the right kind of power for your battery? It's not just magic, it's science. And a huge part of that science relies on a tiny, incredible component that acts like a traffic cop for electricity. Think about a one-way street in a busy city. Cars can only go in one direction. If a car tries to go the wrong way, well, it causes a big problem. Traffic stops, horns blare, and nothing gets where it needs to go. It's a simple rule, but it keeps everything moving smoothly and safely, ensuring that chaos doesn't take over the streets. Now, imagine that instead of cars, we're talking about electricity. Electricity is just a flow of tiny particles called electrons, and they love to move. But sometimes we need to control exactly where they go. We need to tell them, hey, you can go this way, but you absolutely cannot go that way. This control is super important for almost every electronic device you can think of. Without these traffic rules, the delicate circuits inside our gadgets would get scrambled. The flow of energy needs a director, a gatekeeper. This is fundamental to making our technology work reliably day in and day out. This is where our story really begins. We need a device that can enforce this one-way rule for the flow of electric current. Something that says yes to electricity, trying to pass in the correct direction, but puts up a giant stop sign if it tries to sneak back the other way. This simple yet brilliant concept is one of the building blocks of modern electronics. It's a component that, despite its simplicity, enables incredible complexity. It's the unsung hero working silently in the background, making sure the electrical symphony inside your devices plays in perfect harmony, preventing a cacophony of misdirected energy. So what is this amazing little traffic cop? It's called a diode. That's D-I-O-D-E. A diode is an electronic component with two terminals that conducts electricity primarily in one direction. It has low resistance to the current in one direction and high resistance in the other. Think of it like a bouncer at a very exclusive club. The bouncer's job is to let people in, but not let them out through the same door. In the world of electronics, the club is your circuit and the people are the electric current. The diode stands at the entrance, letting the current flow in one direction. We call this the forward bias, but it completely blocks it from going in the opposite direction, which we call the reverse bias. A diode itself is usually a tiny little thing, often a small cylinder with two wires or leads sticking out of it. One end is called the anode, and the other is the cathode. To make it easy to tell them apart, there's usually a stripe or a band on the cathode end. The current flows from the anode to the cathode. So the stripe is like a little arrow pointing against the flow saying, current stops here. How does a diode actually perform this amazing trick? The secret lies inside in its material structure. Diodes are made from semiconductor materials, usually silicon. But it's not just a plain old piece of silicon, it's silicon that has been specially treated or doped to create two different types of regions right next to each other. One side is called the P-type region, and the other is the N-type region. The P stands for positive, because this side has an abundance of holes. The N stands for negative, as this side has a surplus of free electrons. When these two regions, the P-type and the N-type, are brought together, something remarkable happens right at the boundary where they meet. The extra electrons from the N-type side are naturally attracted to the empty holes on the P-type side. So, right at the junction, electrons jump across to fill the holes. This creates a thin layer right in the middle that has neither free electrons nor holes. It's a neutral zone, and we call it the depletion region. This region acts as a barrier. If we connect the positive terminal of a battery to the P-type side and the negative terminal to the N-type side, this is our forward bias. The electrons on the N side are pushed toward the junction, and the holes on the P side are also pushed toward the junction. This pressure shrinks the depletion region, the barrier gets smaller, and poof, the electrons can easily jump across, and current flows through the diode. But what if we flip the battery? Now we connect the positive terminal to the N-type side, and the negative to the P-type side. This is reverse bias. The battery pulls the free electrons in the N region away from the junction and pulls the holes in the P region away from the junction as well. This makes the depletion region much wider. The barrier becomes so big that almost no electrons can cross it. The current is blocked. So the main advantage of a diode, its primary superpower, is its ability to convert alternating current to direct current. The electricity from our wall outlets is alternating current, which means it constantly switches direction back and forth. But most of our electronics, like laptops and phones, need a steady, one-way flow of direct current power. Diodes are the key components in a circuit called a rectifier, which basically chops off one half of the alternating current wave, only allowing the current to flow in one direction. It's kind of like a filter that turns the wild back and forth flow of alternating current into a more manageable one-way pulse of direct current. Another fantastic superpower is circuit protection.